Well, if there's one thing I've learned teaching math, it's that people hate proving things. So they want you to prove something here. The way I guess I'd recommend, if you don't like proving things, just pretend like you don't know the answer, try to find it yourself, and your answer should match what it is that you're trying to prove. How about that? So I'm going to look at this as figure out where f is increasing and where f is decreasing. I'll give you a hint. It's increasing everywhere. But pretend you don't know that if you don't want. And go about your business trying to show where f increases and where f decreases. So you need to find critical numbers. You need to know where f prime equals 0, where f prime is undefined, and endpoints. Endpoints aren't particularly useful here because this graph will be defined no matter what x value you put in. You'll be able to get a legitimate y value back. It's a little freaky with that square root. Well, what if I get a negative in the square root? You won't here because you're squaring it, which turns it, whatever x value you stick in there, it ends up being a positive result anyway. So let's figure out what f prime is. Oh. By the way, this is like saying x times x squared plus 1 to the half. It might be easier to think of it that way, just for using power rule when we do the derivative. Also, f is a product. There's an x factor and a kind of a composite factor here. So to do product rule on it, I'm going to start with just the first thing as is times derivative of second. So the half comes down, the quantity stays the same, the power drops by 1, and we chain on the inner derivative 2x. That is half the product rule. Plus, now we've got to come back the other way. So now we're going to have the second factor as is times the derivative of the first, which is just 1. And if we clean this up a little bit, the 1/2 times 2, this is all part of the first group of stuff that's being multiplied. Half and 2 make 1. We've got an x and another x. That's an x squared. And underneath we've got a square root of x squared plus 1, because it is going to the negative half power. For the second term, we just have square root x squared plus 1. We want this to equal 0. By the way, it will never be undefined for the very same reason that the original function wasn't ever undefined. That is, no matter what you put in for x, even in this radical, even in this denominator, you're never going to get 0, you're never going to get a negative number, due to the fact you're squaring whatever you plug in right away. So we're really just focusing on making the derivative equal 0. I like to, if I got two terms that are equal to 0, slide one of those terms over. So I've got my first fraction is now going to equal, move that over, make it negative square root x squared plus 1. We really have a lot more algebra than calculus going on now. If we multiply both sides by this radical, we get x squared on the left, and negative, look, multiplying a square root by itself will just give you the radicand, the stuff inside the radical. So we get x squared equals, distribute that through, negative x squared minus 1. If you add this x squared over, you get 2x squared is negative 1. Maybe you can see where this is going. X squared, if you divide away the 2, is a negative number. So x would have to be the square root of a negative. That never happens. So we've proven now that the first derivative never equals 0. We know the first derivative will never be undefined, and there are also no endpoints to be worried about. We could say there are no critical numbers. So we could say f prime is always either positive or negative. To figure out what that is, I guess we could say, like, pick a number. I don't know. F prime of 0, for instance, would give you, where's f prime? Would give you 0 over square root 1 plus square root 1 equals 1. That's positive. So f prime is always greater than 0. That means this function will always increase.